there's all kinds of really good learning here to be had about RT Thread and the embedded industry and ecosystem. So I think there's a lot of interesting things going on here today. So one of the things that I would also like to mention really quick about our last talk that was all covering RISC-V by Calista Redmond is that RT Thread is actually in the process of applying for RISC-V membership. So they will actually very soon be also a member of the RISC-V, and obviously they're looking forward to that, and we'll start seeing more and more support for RISC-V processors undoubtedly going into the future. It's as we saw, it's a very big and growing area of the industry, and it's going to be exciting to see where the technology takes us as we look out, the next 5-10 years. So with that, I appreciate everyone taking the time to listen to our session there. We've got 3 more sessions still coming up though today, so don't go away quite yet. We've got a lot of fun stuff going on. The next talk is going to be on research and achievement of RISC-V for embedded MCUs. So we've got more RISC-V coming for you. We've got Yang Yang, who is going to be presenting this particular session. They're the CTO of WCH MicroElectronics, who have also graciously, provided some boards and stuff like that for us. So, or some of the giveaway boards are from their, from WCH MicroElectronics. So I think that'll be pretty interesting talk for all of us. And let me stop sharing my screen here. And let's see here where we are at. I think we're probably ready for the next session here, though. So, all right. So let's get that one queued up for you guys. And I'm looking forward to talking with you all here shortly.
Hello, everyone. I'm Patrick, Technical Director of Nanjing Qinghen MicroElectronics. Today, I will introduce our research and results on RISC-V processor and RISC-V MCU. My report is divided into 4 parts. The first part will briefly introduce the development history of Qinghen, and the second part explains what expansions and optimizations we have made for embedded applications in the process of researching RISC-V. The third part, I will introduce which MCU Plus series products we have MP based on the research results of RISC-V. The fourth part, I will introduce how to create RT Thread project based on CH32V307. Now, I will first introduce the first part, briefly introducing the development history of Qinghen. Qinghen, founded in 2004 years, is an RF and high-speed digital analog mixed IC design company, focusing on connectivity technology and MCU core research. The main products include interface chips such as Ethernet, Bluetooth, low energy, USB, and PCI, and single-chip MCUs integrating the above-mentioned interfaces. The picture is a summary of the development of our company. In the early days of the company's establishment, due to product application requirements, we developed an 8-bit single-cycle RISC core and integrated dedicated interface modules such as USB UART ports, and designed USB 2 series and PD fast charging protocol related products such as CH340, USB 2 serial chip, CH37X series. The above-mentioned product history has gone through more than 10 years of market inspection, and customers' recognition of our products is still relatively high. By 2010 years, we have implemented a single-cycle design of indirect addressing instructions on the basis of the traditional 8051 core, and innovatively bring DMA into the 5.1 architecture and an enhanced version of the 8051 core was designed. RAM access has been reduced from 2 to 1 second. The efficiency was improved by 50% based on this core. A number of cost-effective MCUs featuring USB interfaces have been developed. The cumulative shipments of the above-mentioned series of chips have far exceeded billions. The key point is that they have not encountered a series of command compatibility problems. With the rapid development of custom science and technology, the embedded application field has put forward higher requirements for data transmission speed and operating power consumption. So we introduced a variety of ARM's 32-bit cores around 2012 years, and at the same time continue to innovate and expand in the field of interface connections and develop the 32-bit MCU that integrate USB 2. At the same time, in order to match the needs of high-speed interface applications, we also designed high-speed DMA arbitration mechanism. The company has been paying attention since the RISC-V open source instruction set was officially released in 2014 years. Around 2017 years, due to the security needs of our security products, the company decided to adopt the RISC-V kernel. But at that time, the third-party RISC-V core IP was not yet mature. The core architecture was huge, and it was not optimized for embedded applications. It is not very suitable for our security products. Combining the company's many years of core self-research experience and the company's late product diversification needs, we finally decided to design our own RISC-V core. Next, I will introduce what expansions and optimizations we have made for embedded applications in the process of researching RISC-V. After in-depth research and accumulation of RISC-V, we found that the standard RISC-V instruction set has a flexible scalability and can be expanded and optimized according to the application characteristic of the embedded field. When we were developing low-power Bluetooth products, we found that when the ARM core Bluetooth LE protocol stack was ported to the RISC-V core MCU, the code size was significantly increased after compilation. We carefully studied the RISC-V instruction and found that it is because the standard RISC-V instruction set needs to consider the solidity of the application, and the 16-bit compressed instructions only support word operations, and our actual embedded applications will use a lot of byte and half word operations, which leads to the same protocol stack code. The code size coupled becomes much larger after compilation, and the resources left to customers for self-development are obviously reduced. If you blindly increase the RAM flash resources of the MCU, it will cause the cost of the product to increase sharply. Thus, it will be not competitive in the market. According to the actual situation of our Bluetooth low power, low energy, and Ethernet applications, we feel that adding custom commands that can support half word and byte 16-bit compression C.LBU, C.LHU, C.SB, C.SH. If necessary, we also call on colleagues in the field of RISC-V embedded applications to consider adding this 6-bit compression instruction. After adding the compression command, we did an actual comparison test. Take our Ethernet protocol stack code as an example. After adding customer compression instructions and complying with outer adding compression instructions, the code footprint is reduced by 16%. The IDE which was used in this experiment is Mountain Studio. The IDE is the simple and easy to use embedded integrated development environment based on the GNU version of Eclipse and GCC, and self-developed by the Mountain team based on the RISC-V core. The second problem we encountered in the process of studying RISC-V, PIC interrupt controller cannot meet the real-time requirements of our high-speed interface because PIC is the centralized management interrupt control system. Each privileged mode provides a separate interrupt signal to the kernel. However, MCUs in the embedded field generally do not support all privileged modes. For example, machine mode, user mode, supervision mode. Some may only have machine mode and user mode, and some may only support machine mode. In a single mode of MCU applications, if the PIC interrupt controller with centralized management is adopted, the interrupt preimposition function cannot be achieved. For embedded programs, it is a common operation to set the priority of a peripheral interrupt and require its interrupt to respond in a timely manner. For example, a peripheral data reception compression interrupt is generally set to a high priority, and other interrupts can be interrupted to ensure the real-time data reception. While the PIC interrupt controller cannot achieve a single mode interrupt preemption, so it can't match the real-time application requirements of our current high-speed interface products. In addition, for an embedded MCU, the number of interrupt sources varies from a few to dozens. If a unified entry management method is adopted, it will increase the time for the judgment, thereby increasing the interrupt response delay. Now, I will introduce some comparative experiments we have done for interrupts. As can be seen from the assembly code in the figure. First, enable the interrupt, set the pen bit, send the trigger to enter the execution interrupt function, and use this tick to count. The initial count value is in 0xFF. Count down, set the pen to trigger the interrupt. Read the count value CNT0 before entering the interrupt, and then read the count value CNT1 after entering the interrupt. According to the count difference and the assembly code, the number of cycles from triggering to entering the interrupt is calculated. Although this method may be subject to internal reflecting pipeline and so on, but the data is still representative. Judging from the above actual measurement results, it takes about 41 cycles from triggering to interrupting using the soft stacking method. Most of the time is spent on context preservation. In addition to saving, there is also the recovery time of the register when exciting the interrupt. Theoretically, it takes at least 17 cycles for software to push the stack on a scalar processor. 17 instructions, one cycle per instruction. Plus the time for fetching instructions, the delay is often greater than 19 cycles, but in some low-cost embedded products, software stacking requires at least dozens of cycles. As we can see from our previous experiments on low-power RISC-V processing, at least 41 cycles are required. This is unacceptable in our products with high requirements for real-time interruption. In addition, in some application scenarios that have high requirements for code operation efficiency and low power consumption, the code will be required to run in RAM. However, due to the addressing range limitation of the JAL jump instruction, the interrupt processing function and the interrupt vec table need to be placed in the same storage area. If put in RAM, then all interrupt handling functions need to be put in RAM together. RAM resources are severely limited. If the interrupt, if the interrupt processing function is placed in RAM, the interrupt vec table is placed in flash. When an interrupt occurs, the interrupt number is judged through the unified entry management method, and the interrupt vector of the flash is entered to find the interrupt processing function address, and the JL instruction is used to jump. But the jump range of instructions is plus or minus 1 megabytes, which far exceeds the addressing range of JAL in most storage structures. In view of the large delay in saving context of RISC-V software stack push, more than or equal to 19 cycles, encountered earlier, we designed a hardware push method based on actual applications requirements. We call this HPE mode. Info hardware prologue epilogue. Combined with the optimization of the non-river compiler and toolchain, the following two context-saving methods are designed. One, the context is saved to the register or latch, which increases a certain hardware overhead, but can achieve the lowest response delay. The delay depends on fetching instructions and saving to the stack area. The delay time depends on the time to fetch instructions when an interrupt occurs, and the delay can be as small as 2 cycles. The context hardware is saved to the stack area. Compared with 1, the delay can be at least 17 cycles. The number of hardware gets added is about 2 get counts. In view of the we can see this picture. The PIC interrupt controller described above in our embedded applications. Especially, it cannot match our high-speed applications such as USB 3, SerDes, and Giga Ethernet. We have designed a fast interrupt controller. We call this a PIC based on RISC-V. It can be seen from the schematic diagram that in the PIC we designed, the peripheral interrupts are directly sent to the core. According to the interrupt sent in, there are 2 ways to jump. One, fast interrupt mode. Fast interrupt mode. Look at this. Jump to execute interrupt function by querying the interrupt vec table. To run through unified entry management and further judgment. standard RISC-V processing method to reduce response time. The interrupt vector table can store jump instructions or store absolute addresses. When storing absolute addresses, you can avoid the aforementioned limitation of JAL addressing range. 2. The VTF mode. The VTF mode. VTF info vector table free. That is, VTF does not need to query the interrupt vector table, but directly jumps to the interrupt processing function. That is, when an interrupt occurs, the address of the interrupt function can be directly completed without querying the interrupt vector table, which further reduces the interruption response delay. In our USB 3 and Giga Ethernet applications, this VTF mode is used. Colleagues in RISC-V embedded applications are also called on to wish the colleagues in RISC-V embedded applications to adopt this VTF interrupt handling method. Compared with the previous software stack mode, we did an experiment for only turning on the HBE mode. After enabling SysTick, there is a set pend operation, which is the stallward operation, which takes 2 cycles. After the interrupt, there are 2 instructions to disable SysTick. LUI A5, stallward 0. 2 instructions require 3 cycles. Then, about from trigger to interrupt, SysTick goes through a total of 13 cycles, minus instruction time 13, minus 2, minus 3, about 8 cycles. Compared with the 41 cycles of software stack push, it is about 33 cycles fast, which is actually less than the 17 instruction time. The interrupt response rate is 5.1 times that of the software stack mode. We did an experiment to enable HBE and VTF interrupt at the same time. From the assembly code point of view, the process from triggering interrupt to entering interrupt processing is the same as the program that only turns on hardware push. The count value is here, FF4, which is 2 cycles less in time than mode 1. When only hardware push is turned on, in considering byte alignment in other cases, the VTF interrupt mode does not need to look up the table. That is at least 2 cycles fast, and the number of cycles improved on the embedded low-cost processor. In our USB 3, the Giga Ethernet applications, because the hardware stack and the VTF interrupt mode are turned on, the communication transmission efficiency is significantly improved. The interrupt response rate is 6.8 times that of the software stack mode. In the 32-bit Bluetooth LE MCU applications developed by the ARM core that we introduced in the early stage, there are 2 sleep modes of WFI and WFE. WFI info wait for interrupt, WFE info wait for event. However, importing to RISC-V applications, it is found that the existing RISC-V instruction set does not support WFE sleep mode, and the application breadth is relatively limited because compared to WFE, WFI wake-up sources are limited, and at the same time, it is more demanding for real-time requirements. WFE is more advantageous in occasion because in some application scenarios, we only need to wake up and execute subsequent events directly after wake up. Compared with WFI jump interrupts, it has higher real-time performance. RISC-V currently does not support multi-level sleep mode, which is not conducive to low-power application to adapt to applications with different power consumption and performance levels. For example, the application of the smart TV Bluetooth remote control is in deep sleep mode most of the time. This application focuses on power saving, and the application of the Bluetooth gamepad is mostly in the light sleep state. This application focuses on the real-time communication. Therefore, when designing the RISC-V core for low-power Bluetooth products, we added multi-level sleep modes such as idle, hot, sleep, shutdown, and other sleep levels. In terms of debugging, due to the hardware resources are relatively tight in the embedded field. However, the existing RISC-V products only have JTAG debugging interfaces, which take up more hardware resources and are not very convenient to use. In order to facilitate debugging and maximize the resource utilization, we streamlined the JTAG debugging interface of RISC-V and introduced the two-wire debugging to RISC-V for the first time in the industry. It can reduce I/O resources and take into account debugging speed. This is the RISC-V link debugger, which was designed by WCH. In order to test our expanded and optimize the two-wire debugging efficiency, we did the following comparative experiments. Use the same project code and compiled. Compared with the JTAG of existing RISC-V products, the measured debugging speed is 3.8 times. In order to be able to PK with here we call on colleagues in the RISC-V embedded field to also considering changing the default JTAG debugging mode to two-wire debugging mode, which can save I/O resources while increasing the debugging rate. Now we will introduce our mass-produced MCU products based on the research results of RISC-V. Based on the research on the RISC-V instruction set architecture and the microarchitecture and years of experience in the interface design, we finally formed the MCU Plus product line with 1 core and 3 interfaces as the technical feature. The concept of 1 core and 3 interfaces is shown in the figure on the right. 1 core is based on the self-developed RISC-V core, and the 3 interfaces refer to Bluetooth Low Energy, Ethernet, and USB. MCU with integrated Ethernet interface, 100 GigaMAC and 10 Meg PHY, and Ethernet protocol stacks are independently developed. MCU with integrated Bluetooth Low Power 5.1 interface, including Bluetooth baseband, radio frequency transceiver, and a protocol stack are all independently developed. The MCU with integrated USB interface has a rate of 408 Mbps, and the built-in PHY is all independently developed. In response to different requirements for speed, power consumption, and performance in different embedded applications, we have designed a variety of RISC-V cores and a corresponding series of MCU with integrated professional interfaces. As shown in the figure, V3A V4B, V4C, V4F, and V4F supports floating point operations and memory protection. And the corresponding product is CH32B307. In addition, our innovative general purpose 32-bit RISC-V MCU has Bluetooth LE 5.1 and its product is CH32B208. Main frequency 144 MHz, dual USB. At present, the monthly shipment of MCU products with RISC-V core has reached KK level. Finally, I will introduce our mass-produced MCU. Finally, I will introduce how to create RT-Thread project based on V307 chip. You know, WCH has entered into a partnership with RT-Thread to promote more applications in the RISC-V ecosystem. Now I will introduce how to create a new RT-Thread project based on CH32B307 through River Studio and RT-Thread Studio. First, I will introduce how to create a new project based on B307 by using River Studio. First, select File, New, and River Project in Mars. Interface pops up. Pay attention to check the project template type and chip mode, and click Finish button to complete the new project template of RT-Thread. Next, after completing the compilation, you can use Mars integrated downloading, debugging, and other tools to verify and further develop. When using RTS to create a new V307 project, you first need to confirm that the BSP support package of V307 and its GCC compilation toolchain have been installed. Click this button to open the SDK manager. Click this button. And confirm whether the chip BSP package and GCC toolchain on the WCH are successfully installed. If the red box area is gray, like this, it means that the corresponding resource has not been installed. Click the Install Resource Pack button. By the way, only one resource package can be installed at one time. After the support package is confirmed to be installed, we can create a new V307 RTT project by following the steps below. New RT-Thread project. Note that when you choose to create based on the EVT board, select the correct development board name. At this time, the EVT board information and related menus will pop up on the right side. Just click the Finish button. So the RTT project has been successfully created, just like this. picture. When using mask to compile and download, you can directly use its integrated online download tool. Select the correct chip to download and verify normally. It is more convenient to use, so there's no need to introduce in detail here. But I will introduce the WCH ISP tool download verification after compiling with RT-Thread Studio, and the use of peripheral drivers that can be configured with graphics that are commonly supported. The picture on the right is the information of the peripheral resource that has been loaded. List device timer mailbox. Choose the chip correctly. Allocation of storage resources. Download the program. The newly built template project only contains GPIO and UART drivers and is equipped with a wealth of peripherals. For example, we hope to enable the built-in 10 MAC file and MAC and ADC of the chip. Just click RT-Thread setting on the project. Enter the configuration interface. Click More configurations to see all configuration items of the entire project. We select the ADC and Ethernet operation of options to enable the peripheral drivers of ADC and ATH. To enable Ethernet, we generally expect to use the network protocol stack. The network under the components tab option. Select to enable the LWIP protocol stack. If you want to use functions such as ping and net status of the network port, you can also enable the network interface device after selecting and save all files. Now you can see that the source code of the related peripherals and protocol stacks has been added to the project. Just compile and download. After downloading, you can see that the ATH and ADC related commands have been added. We can try to use them. For example, using if configure to view and configure the current network port information. Ping the offsite network device. Use ADC to sample a certain channel at center. The picture on the left shows the result of adding ADC and ETH related commands on the T-shell. The picture on the right shows the result of using the network interface commands to modify the network IP and ping each other with the computer. This picture shows the result of using ADC to sample a certain channel. The last, I will take a talk about Qingheng ecological plans. WCH will continue to improve our support package and continue to update the related routing packages of Qingheng other chips to facilitate user development and provide developers with a more friendly development experience and a more complete development ecosystem. At the same time, it will continue to work closely with RT-Thread to build a RISC-V development and application ecosystem based on the Qingheng RISC-V MCU and RT-Thread IoT operating system and actively promotes the development of the RISC-V application ecosystem. If you have RISC-V ecological cooperation and technical exchange needs, please scan the QR code here to add my WeChat. Okay, that's all for my RISC-V report. Thank you all. Goodbye.
All right. Well, thank you everyone for attending that presentation. And we certainly want to thank them for taking the time to present to us on that very interesting topic. Now, before